All right. It is 11:01 Eastern Standard Time. So we will get this webinar started. Hello, everyone, and welcome. My name is Jon Sinnreich. I'm the chair of DFI's Seismic and Lateral Loads Committee, and it is my pleasure to welcome you all to today's installment of our webinar series, What's Shaking? The title of our presentation today is Next Generation Liquefaction Database and Probabilistic Liquefaction Susceptibility Triggering and Manifestation Models. The abstract of today's presentation is soil liquefaction and resulting ground failure due to earthquakes present a significant hazard to infrastructure around the world. On a site-specific basis, liquefaction evaluations are performed by first evaluating whether a given soil material exhibits a type of soil behavior in which large pore pressure generation and strength loss is possible. This is the susceptibility analysis, followed by assessing whether the state of the soil and the potential future ground shaking at the site are likely to lead to such strength loss, the triggering analysis, and finally, by considering the potential consequences if liquefaction were to be triggered. The Next Generation Liquefaction NGL project's supported modeling team, SMT, was tasked with the development of new probabilistic liquefaction models. This presentation discusses the SMT's approaches to, number one, use the extensive NGL case history and laboratory test results database to perform analyses that previously would have been logistically impractical, and two, to develop relationships required to compute the probabilities of liquefaction susceptibility, triggering, and ground surface manifestation. The analysis framework developed by the SMT has several elements. First, we assess susceptibility solely in consideration of soil type and behavior considerations and express results in a probabilistic manner instead of a binary yes or no determination. Second, we evaluate the triggering of liquefaction in a manner that distinguishes between what is generally available from case history, such as surface manifestation or lack thereof, from whether liquefaction was triggered in one or more layers, regardless of whether surface manifestation was observed. Third, we introduce a probabilistic approach for evaluating probability of surface manifestation or lack thereof, based on whether a layer within the profile has triggered attributes of soil composition in that layer and stratigraphic information such as layer thickness and depth. This webinar presents the SMT's recommended empirical models and how to easily implement them in practice. Our presenter today is Dr. Kenneth Hudson. Dr. Hudson is a specialist in geology, strong ground motions, and engineering seismology. He obtained his BS in geology and geophysics in 2016 and an MS in geophysics in 2017 from UC Santa Barbara. Dr. Hudson began working in industry in 2017 and simultaneously obtained an MS and Ph.D. in geotechnical engineering in 2020 and 2023, respectively, from UCLA. Dr. Hudson started Hudson Geotechnics, Incorporated, a geotechnical and geologic consulting firm, in 2024, where he works as principal geoscientist. As a licensed professional geologist in California, Dr. Hudson has worked on geologic, geotechnical, and seismic design aspects for high-rise buildings, rail transportation systems, hospitals, schools, and other public and private facilities in the greater Los Angeles area and internationally. Dr. Hudson has extensive geologic field experience and expertise in large-scale computational and statistical analyses for application in geologic and geotechnical problems. Dr. Hudson is involved in geotechnical earthquake engineering research at UCLA and has numerous recent journal publications, such as Relationship Between Fines Content and Soil Behavior Type Index at Liquefaction Sites, and Unsupervised Machine Learning for Detecting Soil Layer Boundaries from Cone Penetration Tested Data. With that, I will turn it over to Dr. Hudson.
Thank you very much for that introduction, Jon, and I'm really grateful to be here, that you guys are hosting me for this webinar, and I'm very excited to dive into these topics of liquefaction with the audience today. This is going to be covering work that I did largely in my dissertation, but it's very much still a living research topic, and we're still working on problems within this this realm and still publishing actively papers on this. And so you'll see over the coming years continued publications within this framework as we push more models out and get more things peer-reviewed and accepted in the literature. So with that being said, since it's such an active topic of research, we're actually conducting lots of surveys whenever we, as our team, the supported modeling team that developed these models, whenever we present our work, we also are trying to collect data on the current state of practice of liquefaction evaluations. And so if you could kindly do so, scan this QR code or put in that URL, and either now while I'm presenting or at the end, and I'll show this this code again at the end of the presentation, go ahead and fill out this survey just to give us an idea. We're trying to understand how liquefaction evaluations are done in practice, you know, across as many different perspectives as we can get, so we can understand how these models that we're actively developing are being applied and how they actually affect the way things are designed and built. So that's part of our research, is to also make it really applicable and understand how it's being done. So if you guys could fill that out when you get a chance, that would really help us out with our continued research. So we're going to dive into our presentation today, and I'm going to introduce a little bit more about what NGL is and the free resources that are available to anyone to use out of that project. The whole database is freely accessible to anybody. And then we'll go into a little bit more introduction into liquefaction itself, the mechanics, how it's typically thought of for evaluating in practice, and then and how it's approached with modeling, how it was modeled in the past, what we call legacy models, and then how we are proposing this different framework for evaluation, and how we got there. So I always like to start off, though, with a quick reminder of why we even spend all this effort and time and money on studying liquefaction. And it's because it's a really widespread hazard. That's just a map of the Los Angeles area with California Geological Survey zones that are potentially liquefiable, that require any project within those zones to be evaluated for liquefaction. So it's a very large, widespread hazard. Pretty much anywhere in the world you go where there is seismicity, or even not, sometimes static liquefaction cases occur. It's just a widespread hazard. And not only that, but it has really devastating consequences when it occurs. And so I put up the famous picture from 1964 and the Niigata, Japan earthquake, where buildings that performed very well structurally during the earthquake failed geotechnically because of the strength loss due to liquefaction underneath their foundations. And so you can see that tilting and sinking back into the ground of some of those buildings that otherwise performed really well from an earthquake engineering standpoint. So we need to continue to understand this, and it still is such a poorly understood phenomenon. So that's why we're engaged in so much active work on it. So I'm going to introduce this concept of NGL, Next Generation Liquefaction, the project, and what the database consists of now. This idea was began in 2014 within the PEER Center, the Pacific Earthquake Engineering Research Center, with the aim of moving liquefaction research forward as a community. So not out of just one research group, but as the entire earthquake engineering community. And at the time, we really recognized that there was a large number of new case histories that were being developed from recent earthquakes, such as Tohoku, New Zealand earthquakes. And we needed to consider those, add them to all the previous case histories that had been used in the past for liquefaction modeling. And it was thought the best way to do that was to follow a next generation attenuation model. If you're familiar with the NGA models that were used to develop the ground motion models, ground motion prediction equations that are used today. It's a community common database that has case histories for use by modelers. So trying to remove the bias in data sets by giving every modeling team access to the same data and letting modelers make the judgment decisions in how they process the data after the fact, but having raw data in an unbiased collective community database. And if we shared that common database, it would overcome some of the difficulties and large disagreements that have been occurring in liquefaction research in the past. And so we wanted to share all those and create this collaborative space where multiple different modeling teams can work out of a common database, right? This has been largely achieved to this point now, over 10 years later from its inception. There have been 2 large technical projects that have been completed now under the NRC in support of developing more new regulatory guidance for nuclear power plants and infrastructure. And as part of those projects and the NGL project at large, the database has really developed and grown quite large. We launched a community-wide collaborative research effort where several modeling teams are now all working out of this same collective data set out of several different locations. And we're now initiating a new technical research project with the Federal Highway Administration as well. And as part of this, we've done a lot of big innovations with this project. As we went along, we found a number of opportunities to improve things. Some of these are the relational database that we developed. It is not only organizing the information efficiently, but it allows us to have efficient interaction with the data through cloud computing, which I directly used in my research using some supercomputer cloud computing to help analyze some of these problems and the large data sets. Second, the nature of some of the case histories, it allows us to evaluate new insights that were not possible in some of the previous liquefaction models. And we've also been able to develop supporting studies, which are just investigations of effects that can't be constrained by the case history data alone, but are critical for model development process, such as like K-sigma effects, large normal stresses, and that effect on liquefaction triggering. And so we've been able to support those studies as well. And then we've also gotten to work on innovative new models and model formulation for liquefaction analysis now. And what's behind all of this is an extensive database that contains information about earthquake events, sites that did or did not experience liquefaction with in situ tests such as borings, CPTs, and geophysical tests, observations, whether there's a sand boil here at this exact location or lateral spreading observed across this area, as well as recordings of ground motions, especially where the ground motions were affected by liquefaction in one of the layers of the site. And then we recently also expanded it to include a bunch of different types of laboratory tests. Of course, all the common index tests you would think of, like Atterberg limits or grain size distribution, but now we also have a big component that hosts cyclic direct simple shear and triaxial tests, and a lot of liquefaction tests within that realm. And the size of this database has become quite large. Here is a plot of the cumulative number of observations within our data set with the year that those observations were made. And so each of those observations can basically be thought of as a case history when it is paired with an in situ test like a boring or a CPT. And so you can see we have several hundred observations and that are next to either a CPT or an SPT plotted in the blue or the orange there. And you can see just how large those are compared to some of the previous data sets that were used for model development and currently used models that are used in practice. And like I said before, this is an ongoing research effort. So if you hadn't had a chance to scan this QR code and get the survey started, please go ahead and do so. But like I said, at the end, I'll come back to this QR code for anyone who hasn't had an opportunity. All right, so we're going to dive into a little bit of liquefaction mechanics so that we're all on the same page about what we're trying to analyze and model here. First of all, to answer the question, what is liquefaction? It's, in its simplest definition, it's just transforming something that is behaving like a solid into behaving like a liquid. And this occurs in soil when we have pore pressure, or we have in the pore space of a granular material, it's fully saturated, it's full of fluid, and then during shearing, we see a pore pressure increase that leads to a decrease in the shear strength. And you can look at this in a very simple experiment at home just by taking two little bins full of sand. One, you saturate the sand completely, and the other you don't. You can put two little fake buildings on top. I'll show that again. And then shake it, and you can see the building that's sitting on top of the wet sand, the saturated sand, experiences much larger deformations than the one in the dry sand. And that's because of the large strength loss underneath the corners of that building where the shear stress is concentrated. Now, how does this happen at a grain size level? What is really happening within the granular material is that if it is contractive in a loose configuration, when it experiences shear, the volume is going to tend to want to decrease. So you see the change in volume is less than zero. The void ratio is decreasing. And in that scenario, we're saying that all the pore pressure is able to stay zero, meaning that pore fluids are able to escape if there were any in this scenario on the left. But on the right, if we have the shearing occur quickly enough that pore fluids cannot escape, then what happens is the pore fluids will push back because they're relatively incompressible. They'll push back on the grains in the sand, and that will eventually cause some of the grains to lose contact with each other, or at least have a reduced normal force on that contact. And in a granular material, it derives its shear strength purely through friction between grains when there's no cohesion. And so if you lose that friction between grains by this increase in pore pressure, you will lose your shear strength. And subsequently, you can experience very large deformations without that shear strength in place. So how do we go about analyzing this in a particular forward predictive case? Well, we break it apart typically into three different problems. We look at susceptibility, triggering, and then the potential consequences. So we can start first with susceptibility, and sometimes this gets called, or things get called susceptibility with varying definitions. There's lots of different takes on what susceptibility means. People will often describe a whole site as, well, is my site susceptible to liquefaction? But what we're trying to do here is come to a common definition, and that liquefaction susceptibility is related to fundamental material characteristics of the soil that control the level of pore pressure generation and strength loss that is possible if the soil were to be cyclically sheared under undrained conditions. So the susceptibility is unrelated to the density of the soil. It's purely the soil type. And its current saturation level of the soil is also unrelated to susceptibility, because both density and saturation are kind of environmental conditions that can change with time. And so we're not going to include those factors in what we call susceptibility. Rather, we're going to break it apart into susceptibility being summarized with two end members: sand-like behavior and clay-like behavior. Sand-like behavior is liquefiable and clay-like behavior is not liquefiable. And those two end members are basically just a frictional, non-cohesive material is sand-like and can liquefy. And clay-like materials will develop their strength through their cohesion and not through frictional physical mechanics and more chemical mechanics. And so those do not experience liquefaction. And there's many different soil properties, index properties that are related to susceptibility that are good indicators of susceptibility. One of the best ones is the plasticity index of a fine-grained soil. And so you can see on this plot here, there's the CRR, cyclic resistance ratio, for a sand-like soil is down here for a low plasticity index. And then there's some transition zone. Sometimes it's thought of as binary with this solid black line, but more recently it's been thought of as a transition zone between sand-like and clay-like behavior, where you're transitioning from a silt to a clay, and the plasticity is changing from low to high. It changes from sand-like to clay-like, and that defines its susceptibility. And there's other things like percent clay content, median grain size diameter, and things like that that can help us determine the susceptibility as well. If we determine that there are susceptible soils at our site, then we can move on to the next analysis, which is a triggering analysis. Now, this is where we kind of throw in things like the density of the soil, the saturation of the soil, and then also the loading that the soil might experience during a design level earthquake. And so the most fundamental way to analyze this would be to actually take, undisturbed samples of your susceptible soils from your site and put them into a cyclic test, whether that's triaxial or simple shear, and apply either constant stress or constant strain cycles to it, and count how many cycles it takes to cause that large strength loss and that pore pressure generation to be a ratio of 1 relative to the initial vertical effective stress. And so that's the best way to understand it, but we do have correlations for when a soil will trigger from penetration resistances in SPTs and CPTs. And then finally, if we determine that there's susceptible soils that are likely to trigger at our site, we need to understand what are the potential consequences are. And this is also very site specific because it depends on stratigraphy, it depends on the characteristics of each layer. But we can predict things like, well, how much ejecta might we expect at the ground surface due to a liquefied layer at depth. How much settlement is a very common analysis. How much lateral spreading displacement might occur. These are all consequences that we need to analyze once we understand triggering at a site. So how do the legacy models, and I just use legacy meaning all the previous models before what I'm presenting today, how do they approach this problem? And the way that they've done this is to develop a case history data set of liquefaction where we store information such as earthquake magnitude and ground motion, typically PGA, at a site where liquefaction did or did not occur. Descriptions of the observations at the ground surface, whether we see sand boils or lateral spreading displacements or nothing. No negative case histories are just as important as positive ones. Information on groundwater and saturation, and attributes of the soil layers, which are typically gotten from in situ testing, because that's the cheapest and the most effective way for especially forward analysis to analyze these things. And the attributes of the soil layer in all these past triggering models have been done on one representative layer within the profile. And so what the researchers would do is, collect an entire CPT or an entire boring, but then just identify the one layer that they believe was responsible for all the liquefaction effects they see at that site, and look at the tip resistance or the penetration resistance within that layer, such as the N160 value, estimate the cyclic stress ratio within that layer, shown on the y-axis here, and then plot points where you did have liquefaction observed at the ground surface or didn't have it observed at the ground surface. And then in this space, it generally becomes separable to some extent between cases that don't have manifestation of liquefaction and cases that do. And obviously, it would be that when you have the higher cyclic stresses and the lower penetration resistances, we get more likely to have liquefaction producing manifestations at the site, and higher penetration resistances and lower cyclic stresses produce lower likelihood of liquefaction manifestation at the site. So that's typically how it was accomplished in the past. And one of the largest pieces of this is the case history processing and critical layer selection that the modelers have to perform in their analysis. And so this is kind of what it would look like in an example. You go out to a site where liquefaction is observed or is not observed. You maybe go a few hundred feet away from this sand boil and say, oh, there was nothing here. And so I'm going to collect a CPT in both locations and compare. But when you go out here and you see this big sand boil, by the way, this is from the 2019 Ridgecrest earthquakes in California, large liquefaction effects out in the desert. We come out and we see the sand boil, and then maybe we collect a CPT at this site, but then we have to determine which layer are we going to use for creating our point on that CSR versus penetration resistance plot. You could come in here and you could say, well, I want to use this layer that's really the shallowest just underneath the groundwater table because it has a low soil behavior type index, I sub C, meaning that it's pretty sand-like, that it has a moderate tip resistance here, and we think it's saturated because it's just below the groundwater table. And then it's also shallow, meaning that if it does liquefy, it has an easier time of punching through this crust and pushing out ejecta onto the ground surface up here, right? But you could also make an argument saying, well, there's actually this layer down here, just a couple more meters down, that has a similar soil behavior type index, similar sandiness, has a pretty similar tip resistance, but it's deeper, so it has a larger crust to punch through. But it's also not right next to the groundwater table, so maybe it has a higher likelihood of being saturated, especially if this is a site where the groundwater table moves up and down a lot, and it might not be 100% saturated right here. It's also a thicker layer, and so it could have larger volumetric strains accumulate within this layer and create a larger force of hydraulic pressure to try and push through. And so it becomes actually very difficult to make these decisions about what would be the critical layer to plot and create our models from. And some Some layers use the critical or use the weakest link approach, where you just purely choose the layer that has the lowest tip resistance that you think is susceptible. Others are trying to consider the stratigraphy and use judgment of all the borings and CPTs around the entire area and understanding of what happened. But most of the time, it becomes a very difficult judgment call. And so here's an example of one case where we ran into this and this difficulty, and we realized that there's actually probably a potential for confirmation bias when you're going through these, because you know in advance when you're looking at these penetration resistance plots with depth, you know which sites did and did not liquefy, and so you might be you might have the potential, even unknowingly, to try and pick a layer that is going to be on the correct side of your model's curve, rather than one that might not be. And it probably doesn't come up that often, but it could be important. And so this is just one example of where we actually chose a layer from this case history that was pretty different from past modelers' selection of the critical layer. And we actually did this exercise for several case histories, 40 case histories, and we had 6 different analysts on our team looking at each of these independently. And we also looked at these blindly, where we didn't know whether manifestation did or did not occur. And we tried to select the critical layers. And you can see the large scatter away from the 1-to-1 line here. And that's just showing that our selection versus the previous modeler's selection does not line up a lot of the time for critical layers. And between analysts, we also don't see much agreement. So we were having some large concerns with this, and it made us actually decide to move away from the critical layer approach, which I'm going to get into how we get around that in just a second. So the first thing that we proposed to try and help us understand this in the modeling framework and start getting around these problems is a Bayesian framework for triggering and manifestation. Let me explain what that means here. So, as I was describing before, these case history data sets include observations at the ground surface of manifestation or no manifestation, and then also a critical layer's properties that are related to its relative densities, such as the penetration resistance. And what is done with the interpretation is that you take the critical layer and you assume that we observe manifestation at the ground surface, therefore the probability that manifestation occurred is equal to the probability of this critical layer triggering. And that's both set at 100% because we observed manifestation here. There's a 100% probability that this layer that we chose in the subsurface to trigger. And it also goes the same for the opposite. When we don't observe manifestation at the ground surface, we would say that, oh, the critical layer we selected from this profile did not trigger. So the probability of no manifestation would equal the probability of no triggering, which in a case where there was no manifestation observed, that would be 100%. But we know realistically these equalities are not valid because we cannot be 100% sure that the layer we select did or did not trigger and is the one that did or did not produce manifestation at the ground surface. So it's better to break that apart into a Bayesian problem where we can analyze whether a layer would trigger, really deep in a profile, and it might be really thin, but did not produce any observable manifestation at the ground surface. So that would be a case where probability of triggering does not equal probability of manifestation. And then we can also have manifestation occur in rare cases when there wasn't liquefaction triggered. But we've seen this happen a few times where it's been assigned as liquefaction at a site, but it actually turned out it was just some large displacements occurring from cyclic softening of a clay. And so we can get large pore pressures, but not fully liquefied pore pressures. in a shallow, thick layer that causes ground cracking or punching failure of footings, but it was really due to strength loss in a clay. So those are some of the cases where we want to break apart these probabilities. And then the way we can achieve this is with Bayes' theorem. And we can set up a series of conditional probabilities to give us a prediction at every site of what the probability of triggering is within each layer. So the way this works and is set up is we can predict the probability that any layer is going to trigger given our observation of manifestation or our observation of no manifestation. And so to predict whether a layer is going to trigger conditioned on manifestation observation at the surface, we need to know what our probability of manifestation occurring conditioned on that layer triggering. So that's kind of an inverse problem. You say, if this layer were to trigger, how likely would it be to produce a sand boil at the ground surface, right? We also need to understand our probability that that layer would trigger in the first place, given the shaking intensity and the density of that layer and its susceptibility. And then we also need to know overall the probability of manifestation, which is a sum of these two equalities down here. I'm not going to get into too much detail on how we break these apart and do this, but this is a framework for how we can estimate every single layer's probability of triggering conditioned on whether we observe manifestation or not at the ground surface. So here's an example of an outlier from Wufeng in Taiwan. There's really large ground shaking here. You can see on this plot here, the cyclic stress ratio in these layers was between 0.4 and 0.5. So pretty significant shaking here. And you can also see that if we were to come and select, from like a weakest link approach, the lowest tip resistance within a susceptible layer at this site, we come up with several layers here highlighted in red that plot at these locations in our tip resistance versus CSR space. And several of these layers would be predicted to liquefy according to this Boulanger and Idris 2016 model. But there was no observation of liquefaction manifestation at this site at all. The SFEV tag here equal to 0, that just means surface evidence, and 0 means none. 1 would mean that there was surface evidence at this site. But how do we reconcile that there are soft sand-like layers at this site, but we did not see any manifestation at the ground surface? Well, this is where we can use our Bayesian equation to calculate this. We can say that the probability of triggering one of these soft sand-like layers is actually really high, given how strong the ground shaking was and how low the tip resistance is. And then we can also look at the profile and say, well, these are really buried underneath this thick clay layer that's almost like 8 meters thick down to the first sand-like layer. And so the probability that manifestation would actually occur due to one of these layers triggering is quite low. Maybe let's say it's 15%, because if it were to trigger, you'd have to see ground cracking all the way at the surface from little displacement you get from these thin, deep layers. So you probably won't see anything. So that probability is low. And then our other part of the equation that we need is the probability that manifestation would occur if there was no triggering in these layers, which that is an extremely low number, right? We wouldn't expect that to happen. And what we can do using this is we can calculate, using those equations, what our probability of triggering and not triggering these layers is conditioned on the fact that we didn't observe manifestation at the ground surface here, right? NM for no manifestation. We actually predict when we carry out that Bayesian equation that we have almost a 90% probability of one of these layers triggering at depth, even though we didn't see surface manifestation. So that's how we set up our Bayesian framework. And then the other problem is still, how do we select one of these as a critical layer for our modeling effort? And so that's where we moved on to our other big framework change, and that's going into a profile-based framework. So the way we do this is we're going to look at, instead of just one or even multiple critical layers from one profile, we're going to create a procedure that looks at every single layer in our profile and accounts for contributions to surface manifestation from every single layer. And the way we achieve this is with assigning probabilities of susceptibility of every single layer. So you'll see this notation, P for probability of in the brackets, and S is for susceptibility, with the subscript L meaning for a specific layer. So we do that for every single layer. We look at the probability of susceptibility, and then we look at the probability of triggering of a given layer conditioned on the susceptibility of that layer. So we could say, well, if we think that this layer is purely sand-like, what is the likelihood that it triggers? And if you multiply these two together using Bayesian statistics, you get a probability of triggering of that layer. And so we can establish those as Bayesian priors from laboratory tests, which we have a large data set of. And then we can assign the probability of manifestation conditioned on each layer triggering. What is the probability that that layer would produce manifestation? And if we multiply all of these three probabilities together, it produces a probability of manifestation of a given layer. And then we can do a product sum of the complements of those probabilities of manifestation, and that produces a probability of manifestation of the entire profile. So we go step by step through every single layer. What is its probability? Do a product sum of 1 minus that value, and then that gives us our final profile manifestation potential. That's kind of the large overview. I'm going to go through an example problem just to show, because it makes it a lot easier to understand how this gets calculated in a step-by-step fashion. So here's a CPT sounding. You can see that we have the layered data here with tip resistance and soil behavior type index, and then also our estimate of CSR and maybe an estimate of CRR from a previous triggering model. And we can look at, maybe this particular layer. Oh, look, there's a low tip resistance and a fairly large CSR here. So that's maybe where it would plot. But then there's this deeper layer here that has higher tip resistance, but a much larger, it has a larger tip resistance, but basically the same CSR. So, we have several different pieces here, but we want to understand in our step-by-step procedure all of these pieces. So first, we're going to look at susceptibility of every single layer. And so the way we calculate this is we came up with this logistic function, which gives us a probability of susceptibility from 1 to 0 based on the soil behavior type index in this case. And so low I sub C gives us a sand-like material with a high probability of susceptibility, and a high I sub C, which is clay-like, gives us a low probability of susceptibility. And we created this as a Bayesian prior using several different susceptibility models in the past that were related to I sub C. And so we combined the uncertainties of all these past models into this Bayesian prior for our model. And what we can do with this is we can look at every single layer's I sub C value, and we can evaluate what the probability of susceptibility of that layer is here. So you can see step by step each layer. There's some layers that are more susceptible, some that are less susceptible as we step through the profile. And it's entirely just a function of the I sub C. Then we can evaluate the triggering of every single layer conditioned on susceptibility. So this is assuming that it's a purely sand-like material and it is susceptible. What is its likelihood to trigger? And we developed new triggering models based on a big laboratory data set that was compiled for this. And we used this laboratory data set triggering model as a prior again within our manifestation model. So it gets updated to a posterior in our final model, taking into account field effects that aren't accounted for in the laboratory-based model, but we were able to develop this model from laboratory tests. That's a function of the CSR, or in this case, we just predict a CRR based on the relative density, which we can relate to either CPT tip resistance or an SPT blow count. Then we can calculate that probability of triggering condition on susceptibility everywhere through the profile here, which you can see it's a really high probability of triggering given susceptibility because this CSR is so much higher or is very large at this site relative to what the tip resistances are. So you can see we have a really large probability of triggering given susceptibility. You can see here we're actually multiplying this by Ksat. This is our saturation term. If we're above the water table, we say that it's not saturated. If we're below the water table, we say we are saturated, but we can also treat this as a probabilistic value rather than a binary solution as well. But we produce that triggering, and then we can multiply this column here by our susceptibility column, and that produces a probability of triggering. And so you can see above the groundwater table, right, we have 0 probability of triggering. And then when we get below the water table, we have several of these layers up here that are very likely to be susceptible and also very likely to trigger. So they have a very high likelihood of triggering. And then some of these non-susceptible layers or lower susceptibility layers have a lower susceptibility of triggering or lower likelihood of triggering. And then we evaluate manifestation. And we tried out lots of different models for this in our regressions. But what we settled on was a fairly simple model that just takes into account the depth of the target layer and the I sub C of that layer as a proxy for hydraulic conductivity and how much ejecta it might produce. And so that's the two variables in this equation. And we predict a probability of manifestation conditioned on triggering. And you can see here that low I sub C's are these blue colors, so sand-like materials are up here. And so sand-like materials are more likely to produce manifestation if they do trigger than clay-like materials are. And then in addition, you can see each of these contours of I sub C decreases with increasing depth. So the depth to the top of the layer, Z top, generally we find that when we go deeper and deeper, it gets harder and harder for manifestation to occur, even if that layer does trigger. And so we can evaluate that here on the rightmost column with the probability of manifestation conditioned on triggering. Where our shallow layers are much more likely to manifest if they trigger than our deeper layers. And then we need to combine those pieces all together to get one probability of manifestation for each layer. And this is where we take into account the thickness of each layer as well, because that's an important aspect for whether it will manifest or not. This is a little funky with this T over TC. I'm going to explain that in just a second, but you can see that we can combine all these pieces in that T over TC exponent to produce a probability of manifestation of every single layer. And then we can do that product sum of the complements to produce a probability of manifestation of the entire profile. Oh, sorry, that's a little off there. But to explain that T over TC really quickly, it basically just allows us to normalize a layer by a characteristic thickness based on, so that it's not sensitive to how you discretize your profile. So here's an example of where a model would be sensitive to your discretization of your profile. If you have this profile that has a 3-meter thick layer, and then this profile too, where you take the same layer, but you say, I'm going to actually break it up into 3 layers for my analysis and analyze each one. If you don't include this T over TC exponent, then when you take the product sum of each of these layers, you actually will produce a different result. If you just multiply these all together, you would get a 50% probability of manifestation. But if you include the T over TC exponent, it doesn't matter how many layers you break this into and then do the product sum, you will always arrive at the same probability manifestation of that layer. So it allowed us to include thickness in our model while making it insensitive to how an analyst might discretize their soil profile. And that's just how that T over TC exponent changes it, so that if you have a thicker layer than your characteristic thickness, it produces a larger probability manifestation, and if you have a thinner layer, it will suppress the manifestation potential of that layer. Anyways, once we do that product sum and take into account the T over TC exponent, we can predict an entire probability of manifestation of the entire profile, PMP, rather than just layer specific. And for this particular example, we would predict an 82% probability that the profile would manifest. So that's generally how our framework works. And this is just a recap again of it. We include saturation, susceptibility, triggering, and manifestation. That all gets added together into one probability manifestation for each layer. Now, how did we go about actually getting the parameters for our models? I talked about susceptibility and triggering both had priors, but our manifestation giving triggering, we didn't give it any prior information, and we let it regress purely based on the data set, and it all updated to posteriors using a Bayesian inference regression. And we used it by maximizing or minimizing this likelihood function that you can see here. We don't need to get into the math, but basically we could reconcile observations of liquefaction or manifestation or no manifestation with our prediction of probability and manifestation for each profile. And so that's how we were able to optimize our cost function and come up with optimized model coefficients that matched our case history data set well. So speaking of that, let's get into how we process our case histories. You guys saw a plot similar to this before, but basically our NGL database has these sites where we have in situ tests, observations of manifestation, and then we also estimate the ground motion intensity measure at those locations, which we actually spent a fair amount of time coming up with a new technique for estimating this. We do some kriging interpolation on the ground motion residuals at the liquefaction case history sites. And we have some publications on this, and Renman Patel was a great aid in this and helped really push it up to a really high level for this analysis. But basically, we came up with new estimates of ground motion intensity measures for all the old case histories as well as all the new ones based on recordings in the area and information about each event. Came up with new ways for interpreting CPTs. Came up with a new relationship between fines content and the I sub C value, because that clean sand correction is pretty important on your tip resistance. And so we came up with a new data set using the NGL data set. You know, we had a much larger collection of co-located fines content measurements from borings with I sub C values from CPTs, and we were able to develop new models and a new model for that and compare it to old models and use that for our clean sand correction. There's our new model, and this is all published so people can use these. And then another big innovation was how we discretize our profiles, and particularly in CPTs. We wanted to have a repeatable, unbiased assessment of where layer boundaries are within the profile. And so we did that with an unsupervised machine learning technique that is just totally repeatable. And this is published, and we have some Python scripts that anyone can use now that are openly available through our website. So you can also use these on your project if you want to do some layer discretization and use our models as well. Those are also included in the Python package if you want to predict your probability of manifestation, triggering, and susceptibility. So just getting into these final updated models after we did these Bayesian inferences, like I said, I used cloud computing and I actually analyzed millions of different potential models with different combinations of layer and profile properties as predictor variables in the manifestation model. And this is what we settled on after millions and millions of different models and potential parameters. We ended up with this model that predicts manifestation condition on triggering using the soil behavior type index and the depth to the top of the layer. And then it also gave updated Bayesian posteriors for triggering so that we weren't not accounting for field conditions for things that might affect the triggering or susceptibility of a soil. And so these are those final equations and kind of what they look like. The red is the prior assumption in the susceptibility and triggering models. And then the black is the posterior that came out of the case history data set. So this is really strongly data driven from case histories, even though it was based on prior laboratory information. And so you can see here, as we might expect, our triggering is actually a little bit, it takes a little bit more to trigger a given layer in a field case history rather than in the laboratory. That's what the black being higher than the red here shows. So there's field conditions and in situ conditions that increase that. And then this is what that final manifestation model looks like. We can kind of look at contours of manifestation condition on triggering. This is the 50th percentile. And you can see that when you go to deeper, to the right is deeper layers and up is higher I sub C layers. As you move this way, you get a lower probability of manifestation. And if you go to shallower and lower I sub C layers, you get a higher probability of manifestation. And we tested this model back on the training data set, and this is what it produced. We had a 72 to 73% true positive and true negative rate, meaning that we're predicting, we are predicting manifestation to occur at locations where it actually did occur 73 or 72% of the time, and then correctly predicting when manifestation does not occur 73% of the time, which is pretty good. And then we can also test this out on other data sets. So for instance, the geotechnical database, the New Zealand geotechnical database, which has a huge amount of case histories from Christchurch. We didn't include all of those in our training data set because we didn't want to bias to one region in the world. We wanted it to be a global model. And there are just so many more case histories in Christchurch than there are in the rest of the world. But what we did was we used their data set as a test for our global model. And we actually produced really good results there too. We actually had a higher predictive rate on this test data set than on our training data set, showing us that we really didn't overfit to our training data set, which is good. And then here's some comparisons to look at how the model translates triggering in a given layer to manifestation at the ground surface. In our traditional, what everyone's used to looking at, our tip resistance versus CSR space. So if we start with a probability of triggering condition on susceptibility of 50%, which is this black solid line here, and then also our 16th percentile, which is often used as like a deterministic curve for your analysis if you don't want to use it probabilistically. That's our 16th percentile of triggering. That's our 50th percentile of triggering. Now, what happens if we evaluate the potential for manifesting that layer if it's buried 3.2 meters down, it's 1.5 meters thick, and it has an I sub C of 1.9. Now, those aren't random layer properties. Those are actually the average layer properties of critical layers that Bollinger and Idris selected for their 2016 model. So on average, their critical layers were 3.2 meters deep, 1.5 meters thick, and had an I sub C of 1.9. And so if we look at, what would their average critical layer predict, it has this lower probability of triggering relative to their 2016 model, right? It takes for a given CSR, it's a much lower tip resistance, or sorry, so for a given tip resistance here, it's a much lower CSR that's required to trigger it, but it actually ends up producing a probability of actually manifesting that layer that's actually a little less conservative. It requires stronger shaking for that particular layer to produce manifestation than the Bollinger Idris model here, at least for most of this space. At low tip resistances, they actually converge to the same value. And we can do this. Now we can kind of deaggregate and look at all these different model coefficients effects on the manifestation potential. So we can start with our kind of deterministic 16th percentile triggering line here. And we can say, well, what if we bury that layer 1 meter with this blue curve here? Oh, then it moves this curve slightly to the left. It's slightly harder to manifest than just to trigger that layer. If we bury it 4 meters, it moves here. If we bury it 8 meters, it moves here. And then by the time you bury it more than 8 meters, it really runs away and becomes almost impossible to manifest. We can also look at the effect of I sub C, right? If we have really a clean sand, I sub C of 1 here, very sand-like, then it's kind of very similar manifestation potential to its triggering. But if we increase the I sub C to 2 and then to 2.3, and then as we keep making it clear, we can see that suppresses the manifestation potential of that layer. And then we can also evaluate the thickness, and we can show that, as our thickness goes from 2 meters to 0.5 meters, as we're decreasing thickness, it takes a larger shaking to cause manifestation of that layer. But actually, as we go to really thick layers, like 6 meters or 10-meter thick layer, it actually becomes easier to manifest that layer than it would be to trigger that layer. And that kind of takes into account that probability that manifestation can occur even without triggering occurring. And it also accounts for the fact that when you have a larger thickness of liquefiable material, if you have like a moderate probability that it would trigger somewhere in that layer, the more thickness you add to it, the more likely that any one point within that layer is going to trigger and cause a cascading effect for the entire layer to trigger. That likelihood goes up, which is why it gets easier to manifest or trigger. So those are our final models. Like I said, this is all published. We have a Nuclear Regulatory Commission report that really goes into detail on all these models, as well as my dissertation. Those are all publicly available. We have a Python module or library that anyone can openly download and then start using for their CPT analyses. And we're currently, we have a couple of papers in review at journals for some of the triggering parts of our priors in our Bayesian inference. And we're also currently drafting some of our final manifestation model papers for journal publication. So that's kind of where we are in the project. And like I said, this is still constantly evolving. And so we want to know how practitioners are using it in different parts of the country, different locations, and different standards of practice, how liquefaction is evaluated. And so it's really great value to us as a research team as we continue to refine our models and make them more usable and applicable for the end user. We need this survey data to assist with that. So if you could take out your phone and scan this QR code, or take this link, and if you look at the slides afterwards, maybe copy and paste this or type it into your browser, then you can fill out that survey for us, and we greatly appreciate it. And we'll be including survey results in future publications as well. So that's the end of the presentation. I wanted to say thank you and open it up for questions and discussion now.
Well, thank you very much, Dr. Hudson. We did have a couple of questions come in from the participants. I'll go ahead and read them out to you in the sequence they came in. The first one was a little bit earlier in the presentation and may have been answered by now, but the question says, when you say no manifestation of liquefaction at ground surface, do you mean sand boils or settlement?
That's a great question, and it's a really difficult one. And it has to do entirely with what case histories are and how we can collect that information. When we define the term manifestation here, we are all inclusive. We're trying to say any type of settlement, any type of total settlement or differential settlement, any type of sand boil, any type of lateral spreading, anything that would cause when a person goes out after an earthquake to a site and say, oh, look, there was liquefaction here that's observable at the ground surface. That's what we're defining as manifestation. Now, the question is, does our case history data set actually capture all of that correctly? And the answer is probably not. You can go out to a free field site and say, look, there's no sand boils anywhere, and I don't see any signs of distress, no ground cracking. There must be no manifestation here. But maybe the entire field, like if you're out on a farm, the entire field settled a foot, but it was a uniform settlement and there was no indication. It was just volumetric strain at depth. There's no indication at the ground surface that that happened. There was no pore pressure sensor at depth, detecting these things. There was no ground motion, strong motion station that showed a change in frequency content of the ground motion due to a liquefaction at depth. There would be no evidence. And so a case history where we might say, oh, there's no manifestation here, might not actually mean that there was no settlement, but that's a limitation of our data set. And we have no real way to overcome that with what we have from our past case histories. And what the observations were made. So to answer your question, that's how we define manifestation, but our data set probably doesn't perfectly match our definition.
Okay, very good. Hopefully that answered the question. Next one is, have you checked the prediction performance of this manifestation model relative to current models like LPI and LSN? And if so, how do they compare?
Yes, definitely. There's a lot of that in like my dissertation, and the NRC report shows those LPI and LSN, and it's similar. It does a lot of similar things, but there's a lot of times it does produce better predictions when you do something like we tested on the Christchurch data set. When we apply LSN to all of the Christchurch data set, and then we look at our model, we do produce a little bit higher, true positive and true negative rates than the LPI and LSN models, but it's not like leaps and bounds better. Those models are still pretty good, but our model just does a slightly better job, and that's just because it's breaking apart more in detail the susceptibility and the triggering and the manifestation potential of each layer. So it's just getting into a little more details on this. So we have done those comparisons, and you can see those in our publications.
Okay, very good. Last question that's come in so far. Hi, great presentation. How would one go from this susceptibility model to applying to settlement predictions?
Yeah, good question. And that's the question we always get asked every single time we present this. And that is our next big goal. We're currently trying to put together proposals for getting, another research contract extending these models into the prediction of volumetric strains and potentially, ejecta settlement. And we're currently in a live project that's funded on lateral spreading displacements. So we're addressing lateral spread displacements. But then for susceptibility, we have a lot of ideas for how to translate this into, or not susceptibility, sorry, for settlement. We have a lot of ideas for how to translate these models into settlement. Even as simple as we can do a first order look by just saying, well, we can look at the Ishihara-Yoshimine volumetric strain predictions based on a factor of safety of liquefaction. We can actually back out a factor of safety of liquefaction from our models, just from the triggering part of our models, right? We can actually back that out for, you know, whether we say it's a 50th percentile is our factor of safety of 1 or whatever percentile we want. We can back out a factor of safety, and then we can calculate a volumetric strain, but then we can weight that volumetric strain by a probability of manifestation conditioned on that triggering. And so that's one way of directly taking the outputs of our model and predicting the settlement. Now, I don't know how well that would actually be validated in real data sets. And that's one of our biggest problems, is there's not robust enough data sets of, you know, observation of this quantitative amount of settlement from liquefaction versus, you know, the case history data set. And so that becomes a difficult thing to validate and know, are we under predicting? Are we over predicting? And so that's something we need to work a lot more on, whether it's going to be with computer modeling or with more laboratory testing on the volumetric strain part of it. That's something we're trying to put together proposals on and how to tackle next.
Okay, are there any other questions for Dr. Hudson? Not seeing any more questions come in. So we're a little ahead of schedule, but I will go ahead and thank you, Dr. Hudson, for this most excellent presentation. Very informative and I think very topical. I believe, Angelina, correct me if I'm wrong, but this webinar will be available on DFI's YouTube channel. It has been recorded.
Yes, it will
Okay.
be available in about a week or two. Meanwhile, they get everything uploaded to our system.
Very good. So if you have any colleagues that could benefit, please let them know, obviously, as well. Would be great to give this as much audience as possible. And I believe, Dr. Hudson, in the presentation, you did have references to your publications, or people, I guess, can just Google your name to search for the relevant publications. And I think with that, once again, thank you so much. Thank you, everyone, for joining us for another installment of our webinar series. And hopefully we will see you all in December at the next one. Have a great day.
Thank you.
Thank you, everyone.